Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Welcome, everybody. I'm very pleased to introduce today's speaker, Guy van Den Broek, who comes to us from the University of Leuven. He has, in a short time, established himself as one of the leading experts, if not the leading expert in, among other things, probabilistic lifted inference, which he's going to talk to us about today. He has won many accolades for this work, including last year, the EKAI Award for the best Ph.D. thesis in AI in Europe. So take it away.
Thanks, Pedro, and thanks for the invitation. I'm really glad to be here. So my talk will be about scalable inference and learning for high-level probabilistic models. And this is the outline. So for the first part of my talk, and the most important part, of course, I'll try to motivate you why I think this is an important area of research and why I think these are important problems. And specifically, I try to motivate why we need high-level representations of uncertainty and why we need high-level reasoning algorithms. So after this motivation, I'll talk a little bit about what do the algorithms do, how do they work, what's the intuition behind them, and then I'll move on to some more theoretical understanding. So what are the strengths and the limitations of these algorithms? And then finally, I'll quickly mention some work that's more practical, that's trying to apply all of these ideas in practice in terms of approximate symmetries and also lifted learning. So first, why do we need these high-level representations of uncertainty? Right. So this is the standard story of machine learning, and specifically graphical model learning. You might have a medical record which contains patients and certain properties, whether they have a cough, whether they have asthma or a bad smoke. So you have this table, and now what you want to do is you learn, for instance, a probabilistic graphical model, such as a Bayesian network. And what this model represents is essentially a probability distribution that says that there is some prior probability that people have asthma, there's a prior probability that people are smokers, and then depending on any configuration of these two variables, there's also a probability that they have a bad cough, right? And now what we've been doing in the last 10 years in machine learning is scaling this up. So when people talk about big data, they mean that we can now learn these probabilistic graphical models and these distributions from very, very large data sets that contain many, many millions of patients, right? So how do we use these models? Well, a new patient comes in and complains, I have a bad cough, and now you want to predict what's the probability that this is due to asthma versus due to smoking, right? And now my Bayesian network might tell you, well, if you observe a cough, then there is a 30% probability that this person has asthma and a 20% probability that this person smokes, and this can then inform your decision-making and the treatment that the doctor prescribes, right? So this is all very standard machine learning, the way we've been doing it for 20, 30 years. But what now if you know more? What now if you know, in addition to all of this information, that Frank, the new patient, is the brother of Bob, and also that Frank is a friend of Dave, right? Now, intuitively, if we know that Bob, the brother of Frank, doesn't have asthma, then we might want to lower our estimate of the probability that Frank does have asthma, right? Because we know that there's some kind of hereditary information there. And similarly, if we know that Dave is a smoker, then we might also want to increase our probability that Frank is a smoker because you know that friends have similar social behavior, right? So intuitively, what we would like to do is, for instance, predict these probabilities here for Frank having these two properties. Now, this is a very basic limitation of the traditional machine learning, is that when we learn these models and when we later use them for predictions, we usually assume that all of these people are independent. So we do not take into account these relationships between the rows in our data, right? And clearly, this is something we want to do because at least intuitively, this is how we reason. This is information that we're losing in the process. And there's this area of machine learning called statistical relational learning where people try to solve this problem. And here the idea is that you really want to augment these graphical models and Bayesian networks with this type of relational information. And there have been dozens of languages proposed in the last decade. And perhaps the most popular one is Markov logic, invented here. And it looks like this. So these are some rules, and they just capture what is in the Bayesian network. So they say that if you have asthma, then there is some probability that you will have a bad cough. And similarly, it says if you smoke, then there's also a probability that you have this cough. And then there are these two weights, and don't worry too much about the semantics here, but the higher the weight, the stronger this dependency is. So this is just capturing the Bayesian network. It's exactly the same information. What we're going to do now is going to introduce these logical variables that refer to the people specifically. So now you say that if a person X has asthma, then this causes this person X to have a bad cough with some probability. And again, it's just saying exactly the same thing, but now it's making explicit the people that you talk about. And now the beauty of this representation is that you can also talk about multiple people, right? So for instance, if you want to model this relational information that says that friends have similar smoking habits, then you just say that if X is a smoker and X is friends with Y, then Y is also more likely to be a smoker. And similar for this hereditary information on asthma, if X has asthma and is family of Y, then Y is also more likely to have asthma. So we have a whole bunch of these representations that are very powerful in expressing these correlations between the rows in our data. And we even know how to handle them. So we know that if we have such a model, like the smokes friends smokes rule here, that this corresponds to a probabilistic graphical model in the traditional sense that we've been understanding them in AI and machine learning. So in terms of a probability distribution, you here have a whole bunch of random variables. They're Boolean, they can be true or false. For instance, whether Alice is a smoker, whether Alice is friends with Bob. So these are all the random variables. And now you have this, you can construct a vector graph or a graphical model that captures exactly this distribution that you're interested in. So for instance, here, if you have these two people, this is the vector graph, and the nodes in such a graph are the random variables, and the edges, they encode a certain correlation. They say which random variables are related. So for instance, this one here, F1, says that if Alice smokes and Alice is friends with Bob, then Bob is also more likely to be a smoker, right? So this is the way that we've been thinking about these statistical relational models for the last decades. I'll give you a little bit of an overview of what goes on in these in terms of these high-level representations of uncertainty. So at the very low level, the basic building block is graphical models, and they've been around for 20, 30 years. And what I just showed you is our statistical relational models, and they're a more general formalism. They capture these correlations between the rows in our data. And then there are two types of representations that are also relevant to my research and very similar to statistical relational models. And the first one is probabilistic databases. And a probabilistic database it's very simple. It's just your standard database. But there's an additional column here that says what is the probability of these tuples in the database. So this database here says that Brando is an actor with 90% probability and that Brando worked for Coppola also with 90% probability. So now what do you use these things for? Well, it's exactly what you use a standard relational database for. You're just gonna write down a SQL query like the one shown here, or you can also write it in first order logic, and you see that it starts to look very similar to a statistical relational model. So for instance, this query here asks for all the people that worked for someone else, all the actors that worked for someone else. And the reason why these representations are interesting is that we have so much text, we have the web, we have very large ontologies from which we can extract all of this information. And the reason why we have these probabilities attached to this information is that we use a lot of statistical machine learning to come up with these facts. So we're never certain about them, but we have some confidence that they hold because of all of the evidence in the text. And for instance, if you use Google, then you might get these info boxes that tell you who is the spouse of Larry Page, and this is just another very large probabilistic database. So I won't talk much more about probabilistic databases today, but most of what I will talk about directly applies to these representations as well. Okay, so that's probabilistic databases, and then really the most high-level representation of uncertainty is probabilistic programming. And probabilistic programming is very powerful and very general. In fact, many of these languages are Turing complete. And one way to think about them is to just take your favorite programming language, Java or C or C++, and think of them together with a random number generator. And the way you normally program these things is that you execute your program once, and then you get a random sample from your random number generator, and then you get just one solution. But instead of executing your program once, now we're going to reason about all the possible executions and the probability distribution over them. This is extremely powerful. And you can think of these graphical models and Bayesian networks as being very low-level sums and products, and they're very similar to hardware circuits. While probabilistic programming is very expressive. It has recursion, it has for loops and while loops, and so on. And so me and my colleagues have been working on this one particular language called Problock. It's a probabilistic logic programming language or data log language. And I'll just give you an example of the type of application that people solve with these types of representations. For instance, if you're a bioinformatician, you have these very large networks, like the one shown there, that model the interactions between genes and proteins. So these are interactomes, and they might tell you that some protein inhibits some other protein with some probability. And now what bioinformaticians want to know is, what is the probability that this protein affects this other protein way down the line? And to solve this problem, you have to compute a probability of there being a certain path in this graph between these two nodes. And this is something you cannot express in graphical models concisely. You cannot even express it in first-order logic or a simple statistical relational language. You really need recursion and iteration here, so you need a programming language. So to answer this question, you have to write down this simple program here and then compute the probability that this query succeeds. And again, this is a very powerful formalism, but also very hard to do learning and inference for. So I won't talk anymore about probabilistic programming, but many of the things I will talk about will also apply here. All right, so that's all these. These are all these statistical high-level representations. These are just representations. Of course, you can now talk about reasoning. How do I make predictions? How do I execute these programs and compute probabilities? And there again, you have the traditional way of doing things, the graphical models world, which has been around for 20, 30 years. There's this very difficult problem of probabilistic program sampling and inference. And then there's this thing called lifted inference, which I'll talk about more today. And then in addition to reasoning, you can also talk about learning. How do I learn a probabilistic program from data? How do I do statistical relational learning, graphical model learning? And then in this talk, I'll also focus on this idea of lifted learning a little bit. So this talk will just be one slice of this whole story of the interaction between high-level representations of uncertainty and reasoning and learning. I'm very happy to talk later to anyone interested in any of these other areas, but I won't mention them anymore today. All right, so now you all know that high-level representations of uncertainty are important, that we need them to model the types of inferences we want to make between the rows of the data. So why do we need high-level reasoning? What's wrong with the algorithms that we have today? I'll try to give you a very simple example. As I told you, me and my colleagues, we work on this probabilistic programming language, and then one day, someone sends in a bug report. And this person tries to build a game, is doing some AI, and he wants to build an agent that plays a card game, and to build this agent, he needs to make predictions about a deck of cards. And he tries to model this, and he sends me a bug report that my code is going out of memory. Okay, so I'm really worried, I'm stressed out that there's some bug in my code, and I'm trying to debug this here, right? So you have the problem is this one here. You have 52 playing cards, and you want to answer some very simple questions. For instance, what is the probability that the first card is queen? It's 1 out of 13, right. Also easy, what's the probability that the first card is hearts? 1 out of 4. Okay, a conditional probability, really hard. What's the probability that the first card is hearts if you caught a glimpse of the card and the dealer did a bad job and you see that actually it has the red color? Yeah, 1/2. And this is the hardest one I could come up with. What is the probability that the last card is spades if the first one is the queen of hearts? 13 out of 51, right? So now you're wondering, like, is this cutting-edge AI research? Should we hire this guy for being able to solve this problem, right? This is a bit disillusioning. Okay, so let's try to build an AI system or a machine learning system that does this. And the standard way of doing this is to use the tools we have. We use graphical models to represent probability distributions. And in a graphical model, what you do is you create a graph, and it has these nodes. So here you see 52 nodes for the 52 positions in the deck of cards. And these 52 random variables can each take 52 values, which are the types of cards in the deck, right? So this is our probability distribution, and we will compute these probabilities I just asked you about, and we'll just look at our textbook and run whatever is your favorite probabilistic inference algorithm. So what's going to happen? Well, to answer this question, you need to know a little bit more about uncertainty reasoning. You need to know this one simple property. Depending on the structure of your graphical model, it might either be very easy or very hard to compute probabilities. If your graphical model looks like a tree, you can compute anything you want very efficiently in time, linear in the size of your graph. it's very simple. If you have a sparse graph, things are still efficient, but if you get a very dense graph, then things become very hard. So this property of the graph is called tree width, and what it essentially encodes is how many conditional independencies are there in your probability distribution. So to answer the question of what happens now, we have to figure out, are there conditional independencies? Okay, so remember this one query. What's the probability that this last card is a spade if the first one is the queen of hearts? So what now changes? The question is there conditional independence? So let's say that we observe the second card. Is the probability going to change? If there is conditional independence, then it's not going to change the probability at all. If there is no conditional independence, then things will change. So what changes if I observe that the second card is the 7 of spades? It becomes 12 over 50, right? So what this tells you is that there is no conditional independence here if you observe this second card. Okay, so maybe we need to observe 3 cards. What happens if we observe this third card being the 4? Then again, things change. So it seems that there are actually no conditional independencies here in this distribution, right? And I could have told you that before by just drawing the graph, because this graph actually has an edge between every pair of nodes. So I spend a lot of time drawing lines here between every pair of nodes. And as you can see, it's really densely connected. And if you run your textbook algorithm on this, variable elimination junction tree, it doesn't even matter which one is your favorite. You will end up building a table with 52 to the 52 rows. So, okay, there was no bug in my system. This is what all the algorithms that we have actually end up doing. These are all of the general purpose uncertainty in AI algorithms. So that was weird and a bit strange that after, after 30 years of research on uncertainty in AI, this is the state of the art, at least for this particular problem, right? Okay, so what's going on here? Why is it so easy for you guys to answer these questions and you thought I was silly for asking them? And why is it so hard for all these algorithms to answer this efficiently? So the answer lies in this example here, right? We knew before that this was the probability for this query here. So what changes if instead of observing the first card, I observe that the second card is the queen of hearts? Nothing, right? Still 13 out of 51. If I observe that the third card is the queen of hearts, again, 13 out of 51, right? So what's going on here is that it has nothing to do with independence or conditional independence or sparsity of the graph or tree width. There's something else here. It's called symmetry, and statisticians would call this exchangeability. And this is a type of high-level reasoning. And when we talk about algorithms that exploit these types of symmetries and exchangeability, we call these lifted inference algorithms. Some other examples. Some of you might know about first-order logic and resolution and theorem proving. This is also a perfect example of lifted inference, where you make inferences about many objects in the world all at once. Here's another example from your high school statistics exam. There's some very rare disease that appears one in every 2 billion women, 1 in every billion men. There are so many men and women in the world. So now what's the probability that more than 5 people have this disease? And okay, it's not so easy to see, but most high school stats students will be able to write down some equation using combinatorics that computes this number. And important to note is that they will not end up multiplying 7 billion numbers, right? They will do something more clever than this. They will do some type of high-level reasoning about uncertainty, some type of lifted inference. So now you're wondering, how does this relate to these statistical relational representations, MLNs? Well, I told you before that if you have such a statistical relational model, like this one here, here we try to classify web pages, and web pages can either be faculty pages or course pages, depending on the link structure of the graph. You say that if X is a faculty page and linked to Y, then Y is more likely to be a course page. So this is just a probability distribution over classes of web pages and the links between them. And okay, this is a statistical relational model. And like I told you, you can turn it into a graphical model, a Bayesian network, or a Markov random field. And if you just do this for 26 pages, you already get this graphical model here, right? It has 700 variables and factors. It's very densely connected. And as you can see, it's also very, very symmetric. And then if you only have 1,000 pages, which is just a very small snapshot of the internet, you already have 1 million variables and 1 million factors in this distribution. And you would just see a large dot here on the slide, right? So if you talk to anyone doing graphical models, they will tell you that this is a highly intractable problem. But then if you do lifted inference and you exploit symmetries, it's just a matter of milliseconds to answer certain queries in this distribution. All right, so now you're all convinced that we need to both have these high-level representations to model all the correlations and relationships between the rows in our data, and also that we need new algorithms that can handle all of these symmetries and high-level reasoning, right? So in the next part, I'll try to show you what do these algorithms do, how do they work, what's the intuition behind them. And to do this, I'll have to introduce a new problem, which is a very basic computer science problem, right? So this is just the simplest problem you can define in computer science that we'll need to solve our problem. Many of you know about set solving. Set solving is just finding a satisfying assignment to a sentence in propositional logic. And such a satisfying assignment is also called a model. And then there's this problem called model counting or sharp set, where you're interested in counting how many satisfying assignments are there to my sentence in propositional logic. So you have this sentence here. It says, if it's rainy, then it's also cloudy. There are 2 variables, and there are 4 joint assignments to these 2 variables. When 3 of them are models, all of them except for the one where it's rainy and it's not cloudy, because that one violates the rule, right? So you have 3 models. The model count is 3. And then there's this version of model counting, which also involves weight. It's called weighted model counting. And here you, in addition to the sentence in propositional logic, you also have this weight function here that tells you that the weight of rain is 1 and the weight of not rain is 2. So now for every world, every satisfying assignment, you can define a weight for it, and then you can sum up these weights to get your weighted model count. And it's very similar to SAT. As you might know, it's hard to find any real-world problems that are SAT. I mean, people have real-world software verification problems and real-world planning problems, but to solve them, they reduce the problem to SAT. And this has enabled us to build very efficient SAT solvers because many of these problems can just be reduced to it. And it's very similar for probabilistic reasoning, where you have all of these representations of uncertainty, Bayesian networks, vector graphs, Markov logic networks, probabilistic databases, and so on. They're all different in fundamental ways, but if you want to compute a probability, then what we have shown in the last 10 years, and not me, but other people, including here, have shown that you can just reduce this computation to a weighted model counting problem. So if you can build an efficient solver for weighted model counting, you can build an efficient solver for all of these problems. Similar to how if you can build an efficient SAT solver, you can build an efficient planner and an efficient verifier and so on, right? All right, so I will not talk about weighted model counting, but about a slight generalization, which is weighted first-order model counting, where the solution is to a first-order logic sentence, like the one shown here. Here it says that if on a day D it's rainy, then it's cloudy on that same day. And this has this quantifier for all, which makes it a sentence in first-order logic. And let's say that you now have one day, Monday. Well, then these are the possible worlds. And again, there are 3 models. It looks exactly the same as before. It gets more interesting if you have 2 days. If you add Tuesday, suddenly you have many more possible worlds. You have many more models. In this case, you have 9 models. And like we had before, now you can associate a weight with certain assignments to variables, and you can sum up the weight of all of these models to get your weighted first-order model count. And now the beauty of this is that, again, if you want to do high-level probabilistic reasoning, what I tried to show, and also others, is that any type of high-level representation of uncertainty you have, it could be Markov logic networks, relational Bayesian networks, probabilistic databases, certain types of probabilistic programs. It doesn't really matter because if you want to compute probabilities, if you want to do learning, you just reduce your problem to 1 or 2 weighted first-order model counting problems and you're done. So what we have to do is we have to build very efficient weighted first-order model counting solvers. So let's build one, but let's also simplify the problem a little bit. Forget about the weights. The weights are totally not interesting. They're just bookkeeping. They are annoying, but they don't change any of the insight. So let's just do model counting of first-order logic sentences. And I'm going to show you a bunch of inference rules which you'll be able to apply backwards to solve pretty complex problems. So here's the first sentence in first-order logic. It says that if Alice has stress, then Alice also smokes. And there's just one person in the world called Alice. So what's the model count of this sentence? So it looks exactly the same as what we had before, right? It looks like cloud and rain. And there are, again, two variables, whether Alice has stress and whether Alice smokes. And there are 4 joint assignments. And they're all models except for the one where Alice has stress and doesn't smoke, because that one violates the rule, right? So now what changes if instead of just Alice, we have n people in the world? Well, now instead of making one decision, we have n decisions to make for all these people, but we can make them separately. They're all independent. So if you want to count the models of this sentence here, it's 3 to the n. You have 3 choices for every person, and you have n people that you can make an independent choice for, right? Okay, this is a weird one. What if there's some special person, let's say it's me, I can be male or female, and if I'm female and I'm the parent of someone else, then I'm also the mother of that someone else. If I'm male, then the sentence doesn't say anything. And again, there are n people, right? So here we have to simplify the problem a little bit. So again, if I'm female, then this is what the sentence says. It says that if I'm the parent of someone, I also have to be the mother of that someone, right? And this looks exactly the same as the sentence we had in the previous step. It's just renaming the relationships. So here we have 3 to the n models, because these are all the possible ways for someone to be a parent and a mother. If I'm not female, then the sentence doesn't say anything, and everything is a model. And then again, we have 4 possible assignments for every person, and then n choices to make. So the total model count here is 3 to the n plus 4 to the n. And then this is the hardest one. What if there's not just me who can be male or female, but there are n people that can all be male or female and can be each other's parent or mother? Well, it's a bit harder to see, but believe me that for all the people x, again, you get an independent problem to solve. You can count for every individual x how many solutions there are. We already know if there's just one person x, that's essentially the same as the previous step. We have 3 to the n plus 4 to the n models. But now we can make these choices n times. So this is here the model count, right? So just to give you an intuition of what these algorithms do, when we have some input, that's this sentence here, it reduces it to the previous one, to the previous one, to the previous one, unless you have a base case, until you have a base case to solve. And then there's just one more inference rule that you have to understand, and then you can build your own lifted inference solver. There's nothing more to it. It's counting the solutions of this sentence here. And the sentence says that if x is a smoker and x is friends with y, then y also has to be a smoker. So how many solutions are there? It's I'd be surprised if anyone could find out, but we'll solve it together. Let's simplify the problem again. Let's say that I tell you precisely who is a smoker. So I give you a database of people, of Alice smokes, Bob is not a smoker, and so on. And I tell you that these specific k people, they all smoke. So now we have to solve a different task. Now we have to count how many possible friendships are there left that given this evidence on smokers, given this smoking database. Okay, so we have to figure out, can these k smokers be friends with these k other smokers? What do you think? Are smokers allowed to be friends with smokers? Yes, right? Okay, so these friendships are allowed, but they're not required. Are the non-smokers allowed to be friends with the non-smokers? Yes, right? Are the smokers allowed to be friends with the non-smokers? No, these are not allowed. Because if you're a smoker, then the rule says that you have to be, that you cannot be friends with a non-smoker, right? So these are all disallowed, and then the last ones are also allowed. So what you get is that there are n square possible friendships between n people, and they're all allowed except for the the friendships between the k smokers and between the n minus k non-smokers, right? So this is your model count. You can make 2 choices for everyone, except for there's friendships between the smokers and the non-smokers. But of course, we don't know precisely who is a smoker. We just get this sentence in first-order logic as input, and we don't get this extra information. So let's simplify it a little bit less. Let's just say that I tell you that there are K smokers, but I don't tell you who is precisely the smoker. Well, now we have to count how many possible databases are there in which K people smoke out of N people in total, right? So now I have to count how many databases could I have given you, and that's N choose K, right? So now this is the model count. And of course, I don't know that there are K smokers. I just tell you that there is this sentence and there are N people, but I know that the number of smokers is between 0 and N. So in total, we have this many smokers here. So this was a little bit difficult, but it's also a very difficult reasoning problem. If you give this problem to a graphical model, it will build, and again, a table with 2 to the n rows. It will just go out of memory. But by reasoning a little bit about the high-level structure, we were able to count this number pretty efficiently. And in fact, we have algorithms that are based on these principles. So this just gave you the intuition. The algorithms are a little bit more complex. What they do is they start from some statistical relational model, like this Markov logic network that we saw before. It models all these intricate relationships in a statistical way. And like I told you, we're gonna reduce this problem to a weighted first-order model counting one, where we take these weights out of the equation, and we just end up with a sentence in first-order logic. And then this algorithm that I developed in my PhD thesis compiles this sentence into an efficient circuit language. And now, given this circuit language, this weight function, and a certain domain of people, now we can compute this weighted first-order model count efficiently. And this corresponds to the partition function of your graphical model, if you know about those. So what should I have answered to this person that sent me the bug report? Well, they were using the wrong tools, right? They were using graphical models, and it was never going to work. What they should have done is modeled this probability distribution over a deck of cards as a relational model. You don't even need a statistical relational model here. It's just a first-order logic. So for instance, this sentence here, it says that in all positions in the deck, there's at least 1 card. That's the first line. Then it says that for all cards, there's at least 1 position in the deck. And then the third one says that for every position, there cannot be 2 cards in that position, 2 different cards. And this is enough to completely specify a probability distribution over decks of cards, very concisely. And then what they should have done is run a lifted inference algorithm on this problem, where the lifted inference algorithm would have told you that the number of models of this sentence is this equation here. And again, it looks a bit complex, but you can recognize the summations, the binomial coefficients, and these powers, very similar to the examples I showed you before. And if you look closer, you can figure out that this equation here, it actually is n factorial. And as you know, the number of possible worlds of a deck of cards is n factorial. It's the number of ways that you can shuffle a deck of cards. So here we get the correct answer. And what's nice here is that you get this correct answer, the number of possible worlds, or the partition function, you get it in time polynomial in n. While before we were building a table of 52 to the 52 rows. So this is an enormous exponential improvement. This is much, much more efficient than what we could do before. All right, so this is how these algorithms work at an intuitive level. So now, what can we say about them? What are their strengths and limitations? And the goal here is, so this was a question that I asked myself when I started my PhD. I want to really understand what is the complexity of probabilistic reasoning, what are the fundamental ideas here and the limitations of reasoning about uncertainty at a high level. And what we had for the last 20, 30 years are these ideas that are all related to graphs and tree width, and they're very good at describing what is going on in the graphical model world traditionally and what all of these textbook algorithms are doing. But I hope I convinced you that they're totally inadequate to describe the type of high-level reasoning that we would like to do, right? So what we need to develop is some new theory of liftability, of when can we do this high-level probabilistic reasoning. And it turns out that this is quite a nice area for theory people because it ends up being very related to database theory, finite model theory, 0-1 laws, counting complexity, and so on. So it goes back to some very fundamental computer science ideas. So I did not invent lifted inference. Lifted inference has been around since 2003 or even before. But the way that it has been around was at a more informal level, where people talk about exploiting symmetries, reasoning at the first order level about groups of objects, doing scalable inference, doing high-level probabilistic reasoning, and so on. So what I proposed in my thesis is a definition, because if you want to do some kind of theoretical analysis, you have to at least define what the problem is, right? So this definition is called domain lifted inference. It's one notion of what lifted inference could mean. And it tells you that some algorithm is lifted if it runs in time polynomial in the size of your domain. So what does this mean, actually? It means that in the examples I showed you before, you might have a social network, and you want to be polynomial in the number of people in your network. You want to be polynomial in the number of web pages in your hyperlink graph. You want to be polynomial in the number of cards in your deck, right? These are all of the entities in the domain. And it's something that's very similar to the idea of data complexity in databases. In practice, this is what you get. So you have some kind of statistical relational model where you, let's say, want to classify web pages. You increase the number of web pages, and then your traditional graphical model algorithm will blow up exponentially with the number of web pages you add. But if you run a lifted inference algorithm, it would, for instance, be linear and scale up nicely with the number of web pages. So this is what you want. And similar, if you have a learning problem where you have a database that you want to learn from, well, if you're going to be polynomial in the number of people, you're going to scale up much better than when you're exponential in the number of people. So you're going to be able to scale up to big data, let's say, in your learning problems. I showed you this picture before. This is one of the algorithms we have. And okay, we have this nice property that if we compute this weighted first order model count, we do so in time polynomial in the domain size. So in fact, these algorithms that we have, they're all domain lifted. They are all able to scale up with the number of people. However, there's a problem. We don't always know what to do. Sometimes you might give me a problem and I tell you, sorry, I don't know how to solve this efficiently. I will just have to reduce it to a graphical model, right? So that's a problem. And then the natural question to ask is, when can we do things efficiently and when can we not? And then there's this theorem, which goes back to this NIPS paper here, which kind of started this idea of proving when things are liftable and when things are not liftable. And this theorem says that weighted first order model counting is liftable for FO2. And FO2 is this class of logics that theoreticians like to talk about, but it's perhaps not the most intuitive. You can kind of restate this theorem to say that if you have a Markov logic network with 2 logical variables per formula, then I can always guarantee you that you will be able to run lifted inference. I can guarantee to you that you will be able to scale up with the number of people in your domain. I can also restate this theorem to say that for certain probabilistic programs with 2 logical variables, they will always be liftable. But still, that's maybe not so intuitive. So let's just look at the types of features that you would use in a machine learning model. And traditionally, if you do machine learning, you have all of these people or web pages or whatever are the entities in your domain, and you have all these properties. For instance, whether they smoke, how tall are they, how old are they, anything you can come up with. The vocabulary of traditional machine learning is just to work with these types of features and then build some model of the world. And now what we try to do in statistical relational learning is to also take into account these relationships between the people and the correlations between the rows in our data. For instance, are people friends and colleagues and so on. And now what this theorem tells you is that it doesn't matter what you come up with. You can make any type of model. You can write down any model or learn any model that makes statements of this form, where you say something about the relationship between 2 people. So for instance, you can say that smokers are more likely to be friends with other smokers. We saw that before. Colleagues of the same age are more likely to be friends. People are either family or friends, never both, and so on and so on. So any statement you can make with this type of vocabulary, talking about 2 people, X and Y, and also any way that you want to quantify this. So you might say that this is a very strong correlation, or this is deterministic, always has to be true, or you can say that this is a very weak correlation. It doesn't matter. You will always be able to apply lifted inference to these types of models. So let's go back to this example here. FO2 is liftable, so what does it say about this model? Well, it applies here. So in this Markov logic network, as you can see, the first rules just use 1 logical variable, and the last 2 rules, they use 2 logical variables, X and Y. So if I get Frank and I want to make a prediction where I do take into account Bob and Dave and all of these other people, then I can guarantee you that I can do so efficiently, and that I can always scale up to big data here and reason about these many people at the same time. So can everything be lifted? Will we at some point be able to build an algorithm that can always scale up in terms of the domain size? And then in collaboration with Dan Suchu, Paul Beam, and Eric Ripkov here, we have this paper at POTS this year that actually shows that no, we will probably never be able to lift certain problems. And in fact, specifically, it says that there is this one sentence in FO3 for which first order model counting is Sharpie1 complete. So this is a bit of technical jargon, and for the people that care about this, this is a complexity class. It's basically counting the number of accepting computations of a Turing machine with only ones on the input tape. And this is class Sharpie1 that actually Valiant introduced, and we can reduce some universal Turing machine for this class to a model counting problem. So that's a lot of technical jargon. What it basically means is that there exists some Markov logic network that has 3 logical variables, and you can go and look at the paper, and see what type of Markov logic network this is. And if we want to count efficiently how many possible worlds this Markov logic network has, or what is its partition function, what is its first order model count, we will never be able to do this in time polynomial in the number of people, unless a bunch of complexity assumptions are violated. So there's also a limitation in what high-level reasoning can do. And then it turns out that this is a quite fertile ground. So me and others have then tried to figure out more of the strengths and limitations of lifted inference. So these are some of the results in the literature. I mentioned this result that says that FO2 is liftable. So all of these models, we can definitely take into account these correlations. I also talked about this one model here. It has 3 logical variables, and we know that we'll never be able to do lifted inference here. But of course, for many of them, we still don't know. You can also analyze this problem in terms of database queries and so on. And I just want to show you this one here. It's this one problem in FO3. It has 3 logical variables, x, y, and z. And it tells you that if x is friends with y is friends with c, then x also has to be friends with c. And this encodes a transitive relation. And it says this graph has to be transitive. This is a sentence in FO3, and we don't know if we can lift it or not. So no one in the world knows whether we can compute the number of transitive graphs in time polynomial in the number of nodes. That's what it says. So if you solve this problem, if you can count efficiently how many solutions are there to this very, very simple sentence, then you solve a very big open problem in this area. So there's still a lot of work to be done. You can also restate this problem in terms of statistics. So just forget about logic, forget about logical variables. They might not be so comfortable for you. Now the question is, what are the statistical distributions, the statistical properties of a probability distribution that will allow you to do inference and learning efficiently? And then there are these 3 properties that are relevant. The first one is independence. And it tells you that the probability of your data set is just the product of the probabilities of the individual rows. A second property is called partial exchangeability. It's less well known in machine learning, but statisticians know it very well. And it basically means that the probability of your data set and some other data set where you shuffled around the rows is going to be the same. So you can just reshuffle the rows and get back the same database with the same probability. And then the third property is called IID, or independent and identically distributed. And this is the assumption that we've been making in machine learning for the last 20, 30 years. And what it basically means is that you have both independence and partial exchangeability at the same time. So these are 3 properties that are relevant. And now we were wondering in this joint work actually with Matthias Niepert here at UW, we were wondering what are the properties of a probability distribution that allow us to do things efficiently. And like I told you, the traditional view in machine learning is that if you want to do tractable learning, you need IID data. And if you want to do tractable inference, then you need conditional independence, low tree width, and so on. Right? So this has been the predominant view. And now what we tried to argue in this paper is that if you want to do learning, you just need exchangeable data. If you want to do tractable inference and make predictions efficiently, then all you need is either conditional independence or some type of conditional exchangeability or a combination of the 2. So in this pursuit of understanding the complexity and the strengths and limitations of high-level probabilistic reasoning, you can also ask these questions in terms of statistical properties. Okay, so this was a whole chunk of theory. So now you're wondering, what is this all good for, right? Well, what does this mean in the real world? And I'll try to give you a brief summary of some recent work in terms of approximate symmetries and lifted learning. So what do you do if you have a statistical relational model that has the transitivity rule in there, and we know that we'll never be able to do exact lifted inference? Or what do you do if you're given a social network that has no symmetries? You're given the Facebook graph, and you assert this into your Markov logic network, and suddenly all of these nice high-level reasoning ideas, they break down, right? What do you do? And so there, we, in some recent work, we're interested in approximate symmetries. So let me kind of reintroduce symmetries now in terms of these grid models here. So you see a grid there, an Ising model that's very popular in vision, where the nodes, for instance, are pixels, and then the edges tell you that neighboring pixels are more likely to have the same color, right? And if you don't know anything about the pixels, then you have a lot of symmetries here. All of the symmetries of the graph are symmetries of this probability distribution. You can just turn this graph around and get back the same probability distribution. So this x and this xg have the same probability. Now, of course, in the real world, you have some evidence that says that, for instance, this top left pixel is darker than this top right pixel, and now all of these symmetries are broken, right? So now, no symmetries, no lifted inference. But you can still talk about approximate symmetries. You can still say that if you rotate this graph, the probability of that picture is going to be approximately the same as the one we had before. And think of all the images on the web. If I ask you which of these two pictures is more likely to be seen on the internet, you won't be able to tell me which one. But I'm pretty sure that one of them is more likely, because people tend to put their hair on one side more frequently than on the other side, right? So one of them is definitely more probable, but I don't know which one. They're approximately symmetric, right? So these are kind of approximate symmetries of images, but they also come up a lot in statistical relational learning and Markov logic. So here's an example of some very real-world, very large classification problem that people do with Markov logic, where you're given the links between a bunch of web pages and also the words on the web page. And for instance, what the model says is that a page X is if it's a faculty page, and it's more likely to contain this particular word hours on it. If X is a faculty page, it's more likely to link to a course page. And then you have 5,000 more of these sentences that tell you how different web pages are linking to each other and what kind of words appear in these web pages. So this is a very large Markov logic network, and if you turn it into a graphical model, it's even larger with many billions of random variables and factors. And the goal here is, of course, to classify web pages. So when you're given all the links and all the words, now you want to figure out what types of web pages are there. For every page, you want to classify it. And this is a classical example of where lifted inference doesn't work. The reason is that every web page will have a different set of words on it, and this graph that captures the link structure is going to be totally asymmetric. So where do these approximate symmetries come from? And then what we try to show here in that NIPS paper is that you can very easily find approximate symmetries in this type of data. So here's, for instance, a database of links between web pages. And by just making small alterations to this database, suddenly you can make things symmetric. So here you've removed one link between Google and Gmail, and you've added another link between AAA and IBM. And suddenly these two tech companies, Google and IBM, they become symmetric. So you can say that these two companies are approximately symmetric. And this matches your intuition, because you know that these are companies in a similar domain, so they are, for you, also approximately symmetric. You can think of this as a matrix. For instance, this is the matrix. That's the standard encoding of a graph in a matrix format. And as you can see, it's very noisy. It's very random and irregular. But then when you do a low-rank matrix factorization, suddenly it becomes very regular and very symmetric. So we can use these low-rank matrix factorizations to find approximate symmetries in our distribution. And then you can plug this into a reasoning algorithm, a learning or prediction algorithm, and this is what you get. So here on the x-axis, you see the time it takes for a sampling algorithm to run, And on the y-axis, you see the error on the predictions, so the KL divergence, it's called. So of course, you want this to go down, and you want this to go to 0 in the limit. Okay, so GIP sampling is a standard textbook algorithm. It's what you would do on the graphical model you get from this Markov logic network. And it converges nicely to the correct probabilities, but it does so rather slowly, right? And then these brown lines here, there are all sorts of what we call over-symmetric approximations. These are probability distributions where we added some links, removed some other links to make the entire problem more symmetric. And what we did here is that we ran a lifted sampling algorithm on this distribution, which has all of these symmetries. And this is the behavior. As you can see, it very, very quickly converges to the wrong answer, right? This is what you expect, because it has all of these symmetries that you can exploit. You can run lifted inference, and things are very fast, but you also changed all of the links between the web pages, so you're getting incorrect results, right? You changed the problem to make it easier. So that's not exactly what we want, but you can get exactly what you want if you plug this into a proposal distribution. So there's ways of constructing sampling algorithms where you take these approximate symmetries and then you exploit them as a proposal distribution. And what you get is that you very quickly converge to the true probabilities by exploiting the approximate symmetries. And this is a way where all of these fancy ideas from exact lifted inference, all of this theory that we developed, basically now give us a very, very useful algorithm in practice that's beating whatever existed before, right? So that was approximate symmetries, which I think is a very promising area of practical lifting. Another example is in learning. So this is a simple problem called lifted weight learning, where you're given a set of first-order logic formulas that tells you what are what's the structure of the connections in this domain. So it might tell you that faculty pages that there's a correlation between faculty pages and course pages being linked together. But you don't know how strong this is. This might be almost always true, or it might just be a very weak correlation. And to figure this out, what you do is you plug in a set of relational databases, and you want to learn this weight from data. And the standard way of doing this is to learn maximum likelihood weights, which involves two computations. You have to compute two numbers, and the first one is just computing how often is this sentence true in the data. That's a SQL query, and people have figured out how to do this extremely efficiently. But the second part is really hard. There you have an existing parameterization of your model, some weights, and you want to compute the expected number of times that you think this formula will be true according to that distribution. And that's basically computing a whole bunch of probabilities at once. And as I showed you, these are very, very hard reasoning problems. So the idea is very simple. Just plug in lifted inference into the computation of this expectation. It's an almost trivial idea, right? And this is what you get. So a very simple MLN, just to show you what is the trend here. You want to learn the weight of this rule that says that smokers are more likely to be friends with other smokers, and you learn from increasing data. So the number of people in your data set is going to increase from 0 to 30,000. And as you can see, the runtime scales up quite nicely, in this case linearly with the number of people. If you would do this with standard graphical models, you would already go into an exponential curve and stop after maybe 4 or 5 people in your data set. And 30,000 people might not sound impressive, but if you think of the probability distribution that you're dealing with here, you're essentially learning a probability distribution over 1 billion random variables, which is all of the possible friendships between these people. So if you like big data, you can think of this as big models, because it's just learning a very, very large probability distribution. So that's weight learning. A much more interesting problem is structure learning. So what if I just give you a set of relational databases and I don't tell you what are the formulas in first order logic that go into this model? So now you have to find both the formulas and the weights. And here the idea is also quite simple. We're going to use symmetry and liftability to regularize our models. And the standard way that machine learning works is that you want to abstract from your data. You want to find a probability distribution that generalizes your data, and that so that you can remove kind of the noise in it, right? And the standard way of doing this is by introducing sparsity, by saying that I'm going to learn a graphical model that has very few edges, so that I know that it kind of generalizes well from the data. And here the idea is that you're going to do exactly the same, but you're going to do it with symmetry. And the idea is that if you find a representation that has many symmetries and that is liftable, it's going to be a very good generalization from your data. Okay, this is what happens. The baseline is the state-of-the-art statistical relational learning algorithm for Markov logic. It works quite well. If you plug in lifted inference to do the weight learning, you get a very significant improvement. So closer to 0 means that you're learning much better models from your data. And then if, in addition, you also learn the structure by using lifted inference to guide your learning algorithm, then again you get significant improvements. So it turns out that symmetry is actually a very good way of regularizing your machine learning models. So that's another example where all of these lifted inference ideas become very practical. All right, so this was my talk. Let me conclude. So I hope I convinced you that this lifted inference business is a very new and kind of a radical change in the way we do uncertainty reasoning. And it's interesting to me because it's a frontier and also integration of many different areas of computer science all at once. So it relates to AI, knowledge representation, machine learning, databases, all different areas of theory. So that's very exciting for me personally. And I think it's also difficult to argue with the need for this type of research in general and this type of direction, because we need relational databases. All of the companies in the world run a relational database system, and in terms of at least the number of entities, all of our data, or most of our data, is relational. And it's also hard to argue with the need for logic, because logic is the foundation of relational databases. And then what machine learning has shown us in the last 20 years is that you also need probabilistic models and statistical learning, because you need that robustness. And of course, we also need algorithms that scale. I think for theory people, there's a lot of stuff to be done here. There are many theoretical open problems, but I also hope that I convinced you in the end that there's a very important practical dimension to this work where we want to apply this to real problems. So for a bit of a long-term outlook, this is for me the shorthand history of uncertainty in AI. So this field kind of started when in '88, Perl showed that you can go from a table, a very large table that captures your probability distribution, to some kind of factorized representation where you use conditional independence to get a very compact representation of a probability distribution, and at the same time build very efficient algorithms that exploit this conditional independence to do efficient computations. And then something that's less well known is that around 2000, a whole bunch of people, including people here actually, figure out that there's another type of structure that you can exploit called contextual independence, or local structure, which if in your conditional probabilities you have a lot of structure, you can exploit this to get exponential speedups again over what was previously possible. And then I hope that sometime in the future, everyone in machine learning and AI will accept that symmetries and exchangeability are just another way to get exponential speedups over what we were doing before, and that we need this type of high-level probabilistic reasoning to make progress in the next step. I should thank all my collaborators who contributed to various aspects of this story, in particular the ones at UW, which helped a lot with, and you know, were very important in many of these papers. And I should mention that there's a prototype implementation of all of this available online, and thank you for your attention.